This lecture is about collections in Scala. This is a Scala collection hierarchy. Overall, there are three main categories: set, map, and sequence. All these classes implement iterable trait, so therefore, all these classes provide a typical high-order function such as for each, or map, or fold, and so on. For set, the default implementation is hash set. So for example, if you create a set of integer, then you automatically create hash set. To create a sorted set, you have to use this sorted set. The default class for map is hash map. So if you create a map from integer to string, like this, you automatically use this hash map. And in order to maintain the order of mappings in your map, then you have to use this sorted map, whose default implementation is a tree map. For sequence, there are indexed sequence and linear sequence. And the difference between these two is, for indexed sequence, you can access individual elements using their indexes, practically in constant time. In the case of a linear sequence, you cannot use indexes to access the element in constant time. For indexed sequence, the most popular class is perhaps a vector. A vector is quite a versatile class. So if your program does not care that much about the performance, then perhaps a vector is the solution that you can use. And arrays are the same as in Java. So they are quite efficient, they are fast, and they come with a very small overhead. Of course, it has its own limitation. For example, in order to double the size of your array, you have to actually create a separate array yourself. For linear sequence, the default class is list. So if you create, for example, a sequence of 1, 2, 3, then you automatically create a list internally. We often use the case construct in Scala to perform pattern matching. And this case is a special keyword in Scala, but it turns out that this case construct is just a syntactic sugar that is translated to partial functions in Scala. A function is partial if it is not defined on some elements in the domain, as opposed to total function, which is defined on every element in the domain. So here's an example. We use this case construct to initialize a variable f. But because this case construct actually creates a partial function, which is just a particular case of a function, you can actually initialize the variable f, whose type is this function type, using this case construct. So it takes a pair of integers and then returns a Boolean. But this function f is partial function, so it is defined only on two elements in the domain, this pair of integers and this pair of integers. So you can apply the function f to this pair of integers and it successfully returns the value true. On the other hand, if you apply the function f to an element that is not included in this case construct, then this expression raises an exception, this match error. Scala has a special class, partial function, to represent the partial functions. It has two type parameters, a and b, and it represents partial function from a to b. So in this example, we are creating a partial function from integer to Boolean. And this partial function is defined only on 3 integers, 0, 1, and 2. So you can call this function f with argument 0 to get the return value true. However, if you call the function f with integer 10, you end up with a match error because 10 is not found in this case construct. One particular feature of this partial function is it has this method isDefined@, which you can call to test if a particular value is contained in the function domain. So this isDefined@, returns true only if the partial function is defined on this argument x. Scala has a for comprehension, which is a very powerful construct in practical programming. So here's an example of using for comprehension. First, from this expression, you create a range starting with 1 and ending with n-1. And this variable I is going to take one of these values starting from the first element 1. And next, we create another range from this expression, which starts with 1 and this time ending with i-1. So notice that the second range is dependent on the particular value for the variable I. And this variable j is going to take one of the values from this range, starting with the first element 1. Now, you have created a pair of variable I and j. And for this particular combination, we evaluate this Boolean expression. In this example, we are testing if this integer I plus j is a prime number. If this Boolean expression returns true for this particular combination of I and j, we yield or we generate this pair I and j as the result. So this particular pair of I and j will be included in the final result of this for comprehension. So we may call the first 2 lines as generators because we actually generate values for these variables. And we can call the third line as a filter because we are filtering some of these combinations of variables I and j depending on the result of evaluating this Boolean expression. In this way, we can easily generate many combinations of these 2 integers, I and j, and then include some of these combinations depending on the result of this filter. To better understand how for comprehension works internally, let's consider these higher-order functions. In this example, we initialize this variable L with a list of integers. We can visualize it as list of integers. And if you call this flatten method, you literally flatten it to obtain a list of integers in the same order. And flatMap is defined as shown here. You first apply the function f to individual list and then call flatten method. In this example, you would call the function f to this individual list and then call flatten method. It turns out that This for comprehension is just a syntactic sugar that is expanded in terms of these higher-order functions. So whenever your class has these higher-order functions, you can use for comprehension on your class. I'm going to use this Scala option type to demonstrate the use of these higher-order functions to translate for comprehension. Scala option type is similar to option type in functional programming. So you can create an option type either with this sum class or with this none. And you can perform pattern matching to test if the option type has some value or if it's just empty. Here's an example of translating for comprehension. In this for comprehension, we have the first generator and the second generator, and we have a filter here. Internally, Scala translated this for comprehension into this expression, which calls flatMap twice. And these flat maps correspond to these generators. And we also see that this yield is translated using this option type. And to understand how this expression works, let's consider another expression shown over here, which replaces flat map with ordinary map. And this expression, it creates an option of integer pair, and then this inner map creates a sequence. So we now have a sequence of option, and this outer map creates another sequence. So now we have a sequence of a sequence of option. This expression works precisely in the same way as this expression, except that it calls flatMap instead of a map. So eventually it flattens it. So the inner flatMap flattens this part to create sequence of integer pairs. So now we have a sequence of integer pairs. And the outer flat map flattened this one again to create a sequence of integer pairs. So in the end, we obtain the sequence of integer pairs. And the reason why you can use this flat map here is this option class also supports for comprehension because it has a flat map. Option class has this flat map method, so you can use for comprehension on option class as well. And it's easy to see why we can actually use for comprehension on option class once you realize that option is just a special case of list which can have only one element at most. That is either a single element or no element. So here's an example. We use this option class, but you can think of it as list of 1 and this list of 2. So we should be able to use this for comprehension. In this case, you can think of none as list of no element or empty list, and you can think of sum of 2 as list of 2. So therefore, you can still use for comprehension, but this time, this list is empty, so therefore, you will not be able to any value for this variable a. So the final result will be empty, but still you can use for comprehension because option is essentially a special class of list, which can have only one element at most.